Hello, welcome to Adistar Lectures on Electronics and Optics. In my last tutorial, you have seen that practically any type of time domain signal you can construct out of the sine terms and the cos terms. If the signal is constructed only using cos terms, so that signal is an even function of time, and if it is constructed using only sine terms, so that signal will be the odd function of time. And if the signal is constructed using both of these terms, that means both the sine and cos term present within the particular signal, so that signal will be neither the odd function of time or the even function of time, rather it will be a combination of them. But using a simple mathematical steps, we can extract the even part and the cos part of the function or of the signal. So that I will demonstrate in this tutorial. In addition to that, here I am going to show you by constructing a time domain signal. So for the time domain signal or for the construction part, I will use the simple Python program as well as the LTSpice. So first of all, I will show you how I can construct a square wave using a simple Python program, and then those frequency components which are used to construct the square wave on my Python program, so those frequency components I will extract out using the Fourier transform, and for that I will use the Python program also. Thereafter, I will show you by constructing the same square using the LTSpice, and that signal also I will extract the frequency components I will extract using the same Python program or the same Fourier transform. At the end of this video, I will show you by extracting the frequency component of my voice and some additional voices. So those are the real-time example of, or the real-time applications of the Fourier transform, what you can do or what is the power of the Fourier transform or the Fourier series. Although there is a very basic difference between the Fourier series and Fourier transform, but we generally call the Fourier series and Fourier transform parallelly, but in case of the periodic signal, we generally apply the Fourier series, but in case of aperiodic signal, we generally are interested to find the Fourier transform. So as I'm demonstrating this video using only the periodic signals, so obviously Fourier series will be applicable much more over here. Fourier transform I will discuss in my later video if possible. So without wasting much time, let's dive into the theory of the Fourier series. The very basic theory I'll discuss, not a very big math I'm going to discuss over here. The time domain signal will be a combination of sine term and cos term, so that's why we can write any function xt will be equals to the summation of the cos terms and the sine terms. Here n goes to plus infinity, but the basic significance of including that infinity is to remind you that the more number of terms you will incorporate to construct a signal, the more accurate your signal will be. Just recall from my last video that when I was constructing the square wave using only 3 components or the 5 components, so there was a ripple in the amplitudes. But when I have used the 50 number of components, so almost a steady amplitudes level we have obtained and a steady square wave we have designed. Although there was a very little ripple, but if you increase the number of components starting from 50 to 500 or 1000, so that the thing I will show you using this Python program over in this tutorial. So you will see that a flat top and flat bottom response you will get for this square wave, and that's the idea of writing this n equals to infinity. But it's not possible to include the infinite number of terms, rather a sufficient number of terms. It means a sufficient number of terms you have to include to construct an accurate signal. Well, so when you are writing a signal in a general term, you have to include both of its odd term and even term. So by incorporating the cos term, you have included the even functions, and if I include the sine term, so that will include the odd terms. So summation of cos terms and the summation of sine terms, if you add them, then the signal will be a combination of both of them. Here, if you are confused with the odd term and even term that I'm referring to these cos and sine terms, so we can easily figure it out, because a signal generally is a combination of odd part and the even part. So any arbitrary signal xt you can write as the x suffix e t, that's the even part, plus the odd part x naught or xo is a function of t, that is the odd part. And thereafter, if you reverse the time, that means if you replace t by minus t, so obviously you will get the x minus t, x of minus t is equals to x of e, xe of plus t minus xo of minus t, xo of t. Why? Because the even part remains positive when you reverse the time, but the odd part becomes negative if you reverse the time, because odd is obviously asymmetric with respect to the y-axis, and that's the thing we have observed in my last video, and that's why this negative term is appearing before the odd part when you are reversing the time. Now if you add them, so you will get the odd part, you will get the even part, and that is this one, and if you subtract them, you will get the odd part, so that one is this one. Now you know that even part is the summation of the original signal plus the time reversal signal of the original function. So now if you do the same thing with your synthesis equation, that means where the xt is defined as the summation of cos terms and the summation of sine terms, and there if you reverse the time, so you will see that only negative sign will appear before the sine terms, and when you will add them, so you will get the cos term, which will be your even part, and if you subtract them, you will get the sine term, so that will be your odd part. So that's why sine term is composing the odd part of the function or the signal, and the cos term is composing the even part of the signal. Well, but here the odd and even part are with respect to the y-axis, whether it is symmetric with respect to the y-axis or not. But what if the signal is asymmetric with respect to the x-axis? As you can see in these animations, when a signal is symmetric with respect to the x-axis, so it has both of the half of equal area above the x equals to 0 and above the y equals to 0 and below the y equals to 0 with respect to the x-axis. But if the signal is asymmetric with respect to the x-axis, so that signal will have a larger area either in the positive half or in the or within the negative half. So if it happens, so that means that signal is basically gaining some DC value. If it gains a positive DC value, so it will shift upwards, having the larger area along the positive half, and if it gains the negative DC value, so it will shift downwards and it will have the larger area within the negative half. And therefore, as you are writing the most general equation of a time domain signal using the sine term and the cos terms, all of these things, so you have to include the DC part. If the DC part is 0, then it will be symmetric with respect to x-axis, and if it is not, it will be asymmetric. So in order to include that, I am incorporating this part. A naught is representing that DC part. Well, so now your synthesis equation is complete. So this is the equation using which you can construct any type of signal, any type of time domain signal, or any type of functions. Well, but here, what are the unknowns? The unknowns are the frequencies associated with the each and every sine term and the cos terms, and the coefficients. Coefficients means the amplitudes, A naught, AN, BN, all of these things. So these things you have to find it out. And you can easily find out what will be the frequency, because if you want to construct a time domain signal, time domain periodic signal, you must be aware of the fundamental frequency. That means the frequency with which you want to construct the signal. So that will be the fundamental frequency, and all other frequencies will be the integer multiple of the fundamental frequencies. Okay. However, but that may not be, that integer multiplications may not be equals to always 1, 2, 3, 4 like this, but it can be an odd integer multiple or even integer multiple, or all both of the odd and even integer multiple. So that's the thing we need to figure it out. So this is the first problem. Second problem is the finding out of these amplitudes, that means A0, AN, BN. But there is a standard procedure that we follow to find out all of these things. But here I'm not going to derive all those coefficients, all those mathematical equations, because it has a straightforward procedure, and you can find the standard procedure in lots of materials available in YouTube and as well as over the internet. So I'm not going to derive all of these equations. Rather, I will just mention what is A0, what is the expression of A0, AN, and BN. So the A0 you can easily write, or you can easily find just by integrating that function over a period. So starting from minus t/2 to plus t/2. And AN you can find if you multiply the cos n omega t on both sides of the equal sign. And you will see that when you are multiplying the cos n omega naught t, omega naught is the fundamental frequency, then the even part, which will be the cos square, and the odd part, which includes the sine part, when it gets multiplied with the cos part, so that will take the form of sine 2 theta. And when you will integrate over a period, so starting from minus t/2 to plus t/2 or 0 to t over a period, so that sine 2 theta term will be 0. Okay, but the cos square term, it will exist. And from here we can easily find out what will be the AN for each values of n. Obviously, for that you need to know what is your time domain signal or the composite signal, and that's the thing you are composing, so you should know what will be the signal. In a similar manner, if you want to find out the BN, you just multiply the sine n omega t, and that sine n omega t will make the even part 0, and it will keep the odd part, that means the terms associated with the BN, and you can easily calculate what will be the BN. And this particular property is called the orthogonal property of sinusoidal signals. So the integer multiple of sine functions or cosine functions, they are orthogonal upon each other. So sine omega naught t is orthogonal over the sine 2 omega naught t, and as well as sine 3 omega naught t, 4 omega naught t. So they are all orthogonal. Orthogonal means they are not coupling with each other. So they are not interfering rather. So that's why we can write the signal or the function using the summation of all cos term and all sine terms, as due to their orthogonal property, they are not interfering with each other. Well, so this is the basic theory of Fourier series, the constructions and the significance already you have seen in my last video and here also. Now, the most interesting part, that I'm going to construct the time domain signal, the sine wave. First I will demonstrate, then the square wave using a Python program, and thereafter I will show you by extracting the frequency component that are used to compose those signals. So let's go. Well, so this is the Python interface that I'm going to use to demonstrate for this video, and the IDE that I'm gonna use over here, and that is called PyCharm, and this IDE is one of my favorite IDE for Python programming. In addition to this, you can use Jupyter Notebook, so that is also a very nice interactive Python shell that you can use. And other than that, Spider is another Python IDE, so that is also my favorite. So, but here for this purpose, I've chosen these PyCharm. Well, so the first block, the imports block, here the matplotlib is for plotting, numpy is for numerical functions, scipy is for scientific functions or some scientific signals are available in this sci-fi module, so that's why I'm going to use this module over here. And another interesting thing is that using the sci-fi module, I can read and write the WAV file or wave file. So that is the audio file that I'm going to use for this demonstration. Well, now next is I'm going to construct a time domain signal. So first of all, I'll show you using only one or two components of sinusoidal signals, and thereafter I will show you using square wave signal having 500 and 1000 components. So that was not available in the interface or the software that I have used to demonstrate in my last video. Well, so here the sampling rate I have used as 48 kilohertz. So that will be the 48K rather. 48K. So this is the standard sampling rate for audio frequencies. In addition to that, another standard sampling rate is 40.1 kilohertz, I think. Okay. So but here I'm using 48 kilohertz, and the duration for which the signal I'm going to generate, that is the 5 second. Okay. So the sampling rate has a unit of frequency, that means the hertz, and the duration is second. Next is a function that I have constructed in order to construct a sinusoidal signal. So there the time domain signal will be generated. So the time signal basically is the function that produces the time domain signal. Next, it's not the square wave, that will be the sine wave first. So it will be sine wave generation. So here I'm using only one component. C stands for component, and F is the fundamental frequency that I'm going to use. So that F is 2 kilohertz over here. Sig1 is the variable that I'm going to use to add up all of those sinusoidal signals. So that I will show you later. But for the time being, I will show you using one sinusoidal signal. And next is the plot of the time domain function. So I'm going to plot that, and that I will show you. And thereafter, when I will demonstrate the time domain signal, then I will go for the normalizations. Why I need to do this normalization? Because the function that I will generate, that I'm going to save in a wave file, and that will be audible. So that's why I have to normalize it in an integer, sine integer format. So that the thing I'm doing using that particular line, and thereafter I'm saving it with the given sampling rate that I'm using, and norm signal is the normalized signal that I have generated over here, and that the thing I'm saving using that particular function, that file name. At the immediate next line, I'm reading that file, that means that wave file just I have saved, and there the sampling rate I'm reading using the sampling rate 1, and I will show you that the sampling rate with which I have saved my file, the same sampling rate it is extracting when you read that file. Okay, so here I need to first uncomment that print. Here it will print the sampling rate 1, and it will show you what it is, because sampling rate already we know that I set it is a 48 kilohertz, and here the sampling rate 1 will be obviously 48 kilohertz also. Next one is the Fourier analysis. Now, here basically, when you are doing the Fourier analysis using computers, we generally do the FFT, not the Fourier transform or Fourier series that we have learned using the continuous time signal. Rather, FFT stands for first Fourier transform, that is associated with the discrete signals. Why? Because obviously, any type of function or any type of signal, when it is within the computer or any digital platform or within any digital media, maybe your smartphone, maybe your iPad, laptop, whatever it is, so they are not continuous anymore. They are converted into digital or in discrete time and discrete amplitude. So that is the digital version of the signal. So although you are observing a sine signal that is continuous, that looks like continuous, but it's not continuous. And my voice, what you are listening right now, as you are listening over the device, over the internet, so that is also digitized. Okay, the Fourier series or Fourier transform that will be associated with a discrete time signal will be different than the continuous time signal, and that is called the first Fourier transform. If you are interested to know what is fast Fourier transform, what is the theory behind them, uh, please put me in a comment box and I can make video on them, but not in this tutorial. So here I'm going to show you, but whatever the Fourier series, the result of the Fourier series will be same with the FFT. FFT is just the discrete version of the Fourier series of Fourier transform that are applicable in continuous function. N stands for the number of samples. So number of samples means out of total time multiplied with the sampling rate. So that will give you the total number of samples that are used to compose that time domain signal. So that is one of the most important thing. And RFFT, RFFT is the right side FFT, because if you, it has a function, SciPhi has the function FFT. If you can use the FFT function also, but FFT will show you both the negative frequency and the positive frequency. But if you see the components within the negative frequency, you will see that they are exact replica of the positive frequency. So they are redundant. So I don't need to portray the redundant frequencies because it's sufficient to observe only within the positive part of the frequency. And practically negative frequency doesn't exist. So that's why RFFT only show you the positive frequency, the components which exist only for the positive frequency. So that's why I have used RFFT, but equivalently you can use FFT functions also. So FFT sig1 is the signal that I just read using that function from here. This is sig1 that I'm using, but here as I'm reading this function, read data, so you can equivalently use that read data. Read data I can use because both of them will be equal to each other. Number of frequency points, this is one of the another important factor that you need to include, because this is the x-axis, the frequency points. At each and every frequencies, your amplitude will be displayed. So that the thing, what will be the frequency points, so that must be converted or must be extracted from this RFFT RFFT frequency, these functions, whatever it is. So here the two inputs are required, say that is the total number of samples and the sampling rate that I have given over here. Next one is the plot. So number of frequency points, this is the x-axis, so x versus y, and y is the amplitude, that the components, the absolute value I have taken because it may have complex values, so we don't need to plot the complex value or the real value. There are other absolute values are much more important, and 2 divided by n, this is the normalizations that I have used over here. If you will go through the theory of the Fourier series, you will see that 2 divided by n is the normalization factor when you will convert it from the time domain to the frequency domain. And the rest of thing is just the associated terms or the functions associated with the plottings. Okay, so these are not so important one, but you can look at these functions if you interested in. So now I'm going to run this one, and first of all, the number of components I set it to 1, and I'm going to run this. So run, and this is the result that you can see. The only one sine functions, that since I have used only one component, so that will produce only a pure sine functions of 2 kilohertz. 2 kilohertz is a fundamental frequency, you remember, and there's no new. Now this is the Fourier transform. Look at here, in this Fourier transform, this only single line that is appearing at 2 kilohertz. Okay, because it has only one component and it is appearing at the 2 kilohertz. Okay. Well, now if you want to listen these functions, how it should okay, the sine wave generated in Python, that is the file name. You can see there's a file name, sine wave generated in Python. That is the file name I have used to save this audio file, and I want to listen it too. So if I play it, I'll request you to lower your sound, lower the sound of it. Yours so loud. So okay. Did you listen that? Well, so this is the 2 kilohertz sine functions. Okay. And if I use, now I'm going to use the two components, but for that I need to change this one. Two components I'm going to use. Look at here. So this is the time domain signal when I use only two components. Okay. One is 2 kilohertz and another is 2 times of that, the 4 kilohertz. And the summation of the 2 kilohertz signal with the 4 kilohertz signal is being done over this particular area that I'm showing over here. Okay. And if I play this one, this file is just changed and lower your volume. Yeah, it almost remains same. And now if I change it to 20 number of components, but with only difference is that I'm not considering the odd components. Okay, so first is the first component, then the third component, because the increment I just changed from the 1 to 2. So if I choose to odd component, oh, before that I need to show you the frequency components. Yeah, look at here. These are the frequency components. So first, this is the fundamental frequency component. It's at the 2 kilohertz and this is the 4 kilohertz. The amplitude I set that is less than the fundamental one, and that you can see over here that this is the, where it is. Look at here. This is the amplitude. So sig, this function is basically is the original signal, and when it gets multiplied with 1 over n, so two components I have used, so that is appearing 1 over n, and that is 0.5, and somehow the amplitude is missing. What is happening? I need to check it. Anyway, so this is the, you can see from here that this is the 50% of the first one. So this is, if it is 1, this is 0.5. Okay. Well, so now I'm going to change the number of components from 2 to say 20, and the increment to 2, because I'm going to take the odd components right now. And here you can see the 20 components is included, but the 20 components are included, but still you can see some kind of ripple is appearing over the amplitude. And here, this is the square, it's forming a square but with a ripple. That's because of less number of components I'm using. 20 components, so 20 number of lines or the spikes that we should observe, and where it should observe, or where the spike should appear. Since the fundamental frequency is 2 kilohertz, so the odd frequencies will be third of the 2 kilohertz, so 6 kilohertz, 10 kilohertz, 7, 14 kilohertz. So let's see. Look at here. So it will be 2 kilohertz, 6 kilohertz, 10 kilohertz, 14 kilohertz, and so on. Okay. And these are the components associated with the 20 number of components. Okay. Because 20 components are not been shown over here, as because the sampling rate are only 48 kilohertz. So if I increase the 48 kilohertz, although I want to mention that this 480 kilohertz is not a standard audio sampling rate, but for this demonstration purpose I can use that thing. And if I use it, it will take a longer time. And look at here, since sampling rate gets increased, so much more prominent is your ripples. As you can see, the ripples exist. Okay, ripple have not died out with the 20 number of components. Okay, and now the frequency components. Let's see. Look at here, all the components to exist: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Obviously, because I'm increasing by 2, so only if you are using the 20 components, so out of the 20, only 10 components will appear in the picture. So basically, the components that I've written over here, that is the 20, but actually the components that is composing the signal, that is only 10, because the odd components I'm considering 1, 3, 5, like this. And in this way, if I construct, or if I use the 200 components, the ripple is much less than the previous one. Okay, and the number of components. look at here the 20 number of components and with gradually decreasing in amplitudes level. Okay, and this is the beauty of Fourier series, that what are the frequency components with what type of amplitude, what amplitudes are used to compose that particular signal that you can extract when you do the Fourier series. But these amplitude levels, they are so large, and that's because of the particular normalizations. Okay, so there are different type of normalizations are used, but the type of normalization that I have used, for that it's coming the maximum value as 40,000. Okay, anyway, so the square wave that I have generated using the simple Python program, and I have shown you the frequency components we can extract. The same square wave you can construct using your LTSpice platform. So here I'm using a simple operational amplifier. This VCC and plus VCC, plus VCC and minus VCC are used for their supplies, and this is the supply. And this is sine wave. And the interesting thing that I'm going to demonstrate over here, the parameter. You can use the amplitude as this A, and this is the special format that you need to follow when you are going to write a parameter instead of a particular value to any of these levels. Say in this case I'm using for the amplitude level and for the frequency level. Here you need to set that parameter within the curly brackets. So here I'm using A to signify the amplitudes, and F within the curly bracket, that signifies the frequency. Okay, and here all of these sources are used same type of formats. So this one is the first, that is the fundamental frequency that it will generate, and it goes with the 1K and 1K. This is the one feedback, and it produces the this is an inverting operational configuration where the output voltage will be the negative of the input voltage, and here the frequency of the signal, that will be of 3 times of the fundamental one, because as you have seen that I am using the odd frequency components to construct square wave. Here I'm also using the same thing, and all sine functions that I'm using, because the phase is 0. If I change the phase from 0 to 90 degrees, so all cos functions will be used. So since I'm using 0 phase, so all the sine functions will be used, and they are going to construct the odd signal, odd square wave signal. Okay, and this one is a 3K and this is a 1K. Why? Because the fundamental frequency had the component of 1, so this one and this one will put the component, the coefficient for the A1 as 1, and for A3 is 1/3, so 1/3 I have achieved using this one. Although you can write A as 1/3, but I prefer to choose this 3 kilo ohm instead of writing this 0.3cc over here. Okay, so this is much more general one. That's why I have used this one. In a similar way, the fifth component, which is the 5 times larger than the fundamental one, I am using 5 kilohertz, 5 kilo ohm resistance over here, and similarly over for the 7th component. But instead of this, only the 7 components, I have used lots of components over here. You can see. Okay, so the 7 components. So this is the 9th, 11th, 13th, 15th, and thereafter also I have used 17, 19, 21, 23 number of components I'm using. Okay, all of these outputs are coming, and they are going to the non-inverting terminal of the summing of this summing operational amplifier, where all of them are get summed, and thereafter I'm exporting that signal into a warp signal. Yes, LTSpice has that power that it can generate a wave file or WAV file, that is the audio file. If you want to extract your sound or your signal into a sound signal, then or audio file, you can save it in this way. So the format is .wav, the path including the file name where you want to save your file name. 16 is the 16-bit signed 16-bit, that the thing I have used in the case of normalizations in Python program. The 16-bit signed, the normalization I have used Okay, so that the thing you have to mention over here, that this signal should be normalized with 16-bit integer, 16-bit signed integer. And the sampling rate here I'm using 44.1 kilohertz. Okay, although you can use 48 kilohertz. Okay, and v naught, which signal or which functions you want to produce or you want to save as a audio function, audio signal. So that the thing I'm using this one, the final output. Okay, so that's why I have to write it over here. Okay, and in addition to that, dot param is the keyword that you must use in order to set the value of the frequency. The value of the frequency is 2 kilohertz, the same value of the frequency that I have used to demonstrate in Python program. Here also I'm using the same thing. And dot param A, parameter A is used as 10 volt. Okay, and dot turn 5 is for 5 second, because in Python program I have shown you by constructing a 5-second square wave or sine wave. Here also I'm going to save it for a duration of 5 seconds. Okay, and now if I run this, and it is going to take a very long time. Look at here. So this is constructing the desired square wave, but you just need to observe this is the progress. Here you can consider it's 1 millisecond. Okay, so 1 millisecond, the simulation speed is 1 millisecond per second. Okay, and the total durations of my generated sine or the square signal will be of 5 seconds. So you can easily imagine what will be the time required to complete the simulation. So 5 divided by the simulation speed, that is 1 millisecond per second. So 5 seconds divided by the 1 millisecond per second. So that will give you the 5 times 10 to the power 3. That amount, that second you need to complete the entire simulation. So that's almost more than an hour. Okay. Well, so after 1 hour, the simulation is completed and the file is saved over here, and the square wave generated in Python, that the same file I put over here with the square wave from LTSpice, and I'm going to run this audio file, and I do request you please lower the sound of your device. Okay. You can listen it, and if I play the square wave that I have generated from the Python, well, just listen carefully these two files and just try to identify the difference between them. Both of them are a 2 kilohertz square wave having duration of 5, but with a very minor or very little difference. The square from LTSpice, Python, LTSpice, Python, LTSpice, Python. Have you noticed something? The thing is that the sound is much more clear in Python, but not in LTSpice. There is a slight, a very small noise present in the square that gets generated from the LTSpice. Just listen once again. So first I'm playing the generated from Python, very clear tone, and now from LTSpice, something is ringing behind the sound and something else. So some noisy nature appears. So I hope that noisy nature we can extract when I will do the frequency, the Fourier series or the Fourier analysis for this particular function, for this particular signal. So let's go to my Python module. Look at here, at this particular one, 44.1 kilohertz it's showing, and because that is the sampling rate, and that the thing it's printing over here, and that the sampling rate is different from the time domain signal that is being generated on the Python module, and that is being generated from the LTSpice module. Both of them are completely different from each other. And look at here, this is the components that gets generated. So 2 kilohertz, 6 kilohertz, 10 kilohertz, these are all of these components. So 23 number of components I have used. So these components are available over here. But if I check very closely around each and every frequency components, look at here. around the 2 kilohertz, two additional components are appearing. And these are the noise frequencies that we are listening. Okay, remember that? And those frequencies are appearing everywhere. I don't know what are the reason for those frequencies, or those unwanted frequencies are appearing over here. I don't know the reason. Okay, because this may be the simulation, or some it's coming from the circuit, or whatever it is. I don't know the exact reason why it is coming over here, but they are coming, and we can identify if I do the Fourier series or Fourier transform, Fourier analysis, whatever it is, whatever the name you can call it, for a particular signal. Okay. Now the most interesting thing that I'm going to demonstrate, that is I'm going to show you the Fourier analysis of my voice. Okay, and this file is the Rudiments of Fourier series part 1 that I have published in last week, and the second one, this the sound that I have extracted from this video. Now I'm going to play this video to identify the timestamp where I spoke in low pitch, high pitch, and in ordinary voice around this particular position. Yeah. This level of low pitch voice, if I generate, so you can see in the frequency domain that the low frequency components are vibrating much more compared with the high frequency component. And if I change my voice from the low pitch to high pitch, you have seen that the around starting from 4 minute 50 seconds to 5 minutes 13 seconds. So that's the thing I'm going to extract. And for that, I'm gonna use the software that is called Audacity. It's a free software, and I think most of you are familiar with this software. It's a very well-known and free software. I'm going to import this audio file, and from my voice, this one. Okay, so this the voice sample that I'm going to copy, and I'm gonna open a new file where I'm gonna paste it. So now, before doing anything over this sound sample, I need to convert it from the stereo channel to mono. So that is available, split stereo to mono. And I'm deleting the second channel. And you can do the analysis, because why I did this conversion from stereo to mono, because the Fourier transform cannot handle the stereo channel. It will be applicable for the mono channel. And here you can do the analysis for the entire time duration for the sound clip, but for the entire time duration, sometime I spoke in low pitch, sometime I spoke in high pitch, and sometime in my ordinary voice. So all type of frequency components will be available, and observing these spectrums, you cannot understand which frequency component will be associated with which time, and which tonal quality. So in order to understand that, I'm going to sample out a very small time duration of my voice, and when I will do the analysis over that small duration, I may assume that within that small time, the frequency components are not varying so much. That means my vocal cord are not varying so much, so that I can get a approximately clear picture of the frequency components for that small time duration. So here, if I extract low frequency components are vibrating, this particular low frequency components, yeah, here if I want to extract this particular tone, because why? As you can see, these sinusoidal signals, they remain almost similar, or almost not varying so much. Is observing the time domain signal, I can comment that there may be two component will be prominent during that particular time. So let's see whether my assumption is correct or not. So now I'm going to copy it, and again another new file, and now here I'm going to export to WAV, and here I'm going to my voice low, and look at here the encoding scheme, that is signed 16-bit PCM, that the same encoding scheme that I have used when I have normalized the sinusoidal or the square wave that I have exported from the Python module to the WAV file, and the same encoding scheme I have used when I have generated the square wave from the LTSpice and to WAV file. And here also I'm going to do the same thing and save. Okay. Now this is the my voice low that appeared, and now I just need to replace this one. This is a file name that that is addressing this one, and I'm replacing this one. And if I run it, look at here, it's the x-axis is ranging starting from 50 hertz to 20 up to 2 kilohertz. And as you can see, the two major components, they are appearing prominent over here. And if I change the semilog, not this semilog x is fine, but if I change this logarithmic to a linear plot, look at here, these two components, these are prominent components that was I was telling. And because this is around, if I put it, you can see this is around 269 hertz and this is around 396 hertz. And if I compare this tone with the frequency analyzer that is available with the software, this plot spectrum, and here also this is also another FFT or the Fourier transform that is available with this one also. And as you can see, by the way, this one is a decibel plot and this one is a linear plot I have plotted over here. And this peak is appearing at 268 hertz and this one is appearing at 269, very close to the one that is showing this the software. And if I take the example, the second example of my high frequency module or of my high frequency voice, so for that I should my voice from the low pitch to high. Yeah, in this way, in this particular portion, I'm going to sample out, and that portion that is maintaining almost constant amplitude, that the thing I'm going to sample it out. And look at here, most probably two major components are there, along with some small components. Let's see. So Control C, new file, and here I need to paste, and I'm exporting to WAV my frequency high, my voice high, and the encoding scheme remains same. Okay, high. That's the thing I'm gonna replace, and now run. And look at here, prominently, very precisely, two components are appearing. One should be around the 500 hertz, another one should be around the 1 kilohertz. And if you remember, the frequency component that I have emphasized during my last video, during my high pitch speaking, and you have seen that the two components were appearing prominently around the 500 hertz and another 1 kilohertz, and these are the two components. And if I compare with the, with the existing facility of the Audacity, look at here, these two prominent components. And here also you can see this is the larger component, this one, which is around 1 kilohertz, and it has a peak of 1.141 and it has a peak of 1.136, almost approximately 1.14. And the second component has a peak around 572 hertz, and here the peak is appearing 572 hertz. So exactly the same frequency components, at exactly the same frequency components, both of them are appearing. So in this way, you can identify for which signal or for which audio frequency, what are the frequency components are used to compose that particular audio signal or audio file. Now I'm going to show you an interesting thing, that is the using a song of a renowned singer, Lataji. Lataji is called the Indian Nightingale, and I'm going to extract the frequency components of her voice for a very small durations. So For that, I'm going to show you that I'm going to take this audio file from Silsila, particularly this part, because ye kaha, during that time, uh, her voice remains at a particular note for a long time, and uh, it will give us the enough time to extract the frequency component for that for her voice. Okay, so it start around 1.47, and as I did for my voice here also, I'm going to split into mono, and I'm going to delete the one channel, and at 1.47 somewhere over here to sample with uh, uniform amplitude. Going to export to WAV file. Just need to replace this file. Now look at it. So this is a very nice peak. Two peaks I'm having. So these two peaks are corresponding to two vocal cord of Lataji during that tone. Okay, and one is appearing around 1.12 kilohertz, and another is appearing at uh, 1.69 kilohertz. So when she was singing, her vocal cords are vibrating these two high frequencies. One is, both of them vocal cords are vibrating above 1 kilohertz. Okay. So this is all about the Fourier series or the Fourier analysis, all about. But although I have given the example of Fourier analysis only using the audio signal, but the Fourier series and Fourier analysis is a very general one, and you can construct any type of signal of any frequency ranges using the Fourier components, or rather in reverse way, we can say that the Fourier analysis holds for frequencies or for the signal having different frequency ranges. That means for micro frequency range, for optical frequency ranges also, you can have the frequency components. You can have the Fourier analysis. Basically, Fourier analysis is applicable where a particular relation holds. For example, in this case, the Fourier analysis exists between time and frequency, where the angular frequency omega is equals to 2 pi divided by t. T is the time period. So when you multiply that angular frequency with the time period, you will get omega times capital T is equals to 2 pi, which is a constant. So wherever such kind of relation holds, there always the Fourier analysis will be applicable. For example, you can take a second example where the wavelength and wave vector are related by the same constant, that is k. The wave vector is equals to 2 pi over lambda. Lambda is the wavelength. That's why a Fourier analysis exists in between the real space and the wave number, and where the real space means the lambda, or the wavelength, where the lambda is measured over the real space and k is the spatial frequency. And in a similar way, when you will study the quantum mechanics, there also the Fourier analysis holds between the position and the momentum space, because the uncertainty of the position and momentum has a lower limit that is equals to h divided by 4 pi, and that is the lower limit, and that is a constant. So that's why the Fourier analysis holds in between the position and momentum. And if you find these videos helpful for you, so please like, share and subscribe, and please make comments if you like this video, and if you don't like this video, please make comments where you and why you are not liking this video. Then your comment will be a suggestion or feedback for my video, and I can make my video much better in future. And you can also suggest me for different topics on which I can make videos for you. Until then, thank you very much. Thank you for being with me.